Before I start, I'm going to be talking about a couple of things. Earlier there was a question about the Google car, the self-driving car. I wouldn't get one either. It's, the reason I wouldn't get one is the guy who started Google, and the guy who were doing all the programming for Google, used to work with me at Bell Labs. And while they're very good programmers, programs typically don't run that well or that often. You find that if you have your laptop, your PC, it's going to crash occasionally. If your PC crashes, you reboot it and everything's fine. If your car crashes, you don't reboot it that easily. So it's really necessary to do more than was done in the past. Back in the 1980s and 1990s, I had a department at Bell Labs that was responsible for testing the equipment before it was put in the telephone network. We had to make sure that the protocols that the equipment used to communicate would operate correctly. We also had to guarantee that the equipment provided by other manufacturers would work with the equipment that existed, so all telephones could call all telephones. One of the guys who worked in my department was Nickolas, the previous guy. And I'm going to be talking about some of the work he did and tell you how to do it right this time. The graduate student who's currently working on this is in the back of the room. So if there's any hard questions, I'm going to make him answer them. Okay, in addition to positioning, which you've gotten kind of used to from the other talks, GPS provides a very, very accurate clock. The satellites in the GPS system have atomic clocks on. They run within a few nanoseconds of each other. You don't get a few nanoseconds down on the Earth because you've got reflections between the buildings, you've got the equipment at the ground station. But you can usually get a clock that's accurate within tens of microseconds at least. Light travels 1 foot per nanosecond, so even if you go 1,000 feet, you've only added a microsecond to the delay. Unlike being 1,000 feet off, in your position estimate, a microsecond isn't that bad. Currently, GPS clocks are used for a lot of things. They're used for international banking, so you put transactions in the proper order. They're used for traffic light control to get emergency vehicles priority. They're used for efficient power distribution on the smart grid. And the most interesting application I saw isn't down there yet. They're using a combination of GPS clocks and a chipset that's been developed by the IEEE to coordinate the time between two relatively close points to get clocks that are accurate within a fraction of a nanosecond. And they're using these clocks to make it more likely that in the particle accelerator beam, well, in Switzerland, they're more likely to hit the atom they're aiming at, even though they're going, it's a mile away. So clocks are actually becoming pretty important. And what I'm going to try to convince you of today is that we can also use clocks to make it possible to prove that automated driving applications aren't going to cause crashes. And the reason we're going to be able to do that isn't because of the clocks itself, but because we're going to be able to design a new class of protocols that depend upon synchronization. Things happen at the same time. And by having things happen at the same time, we're going to find that we can do two things. We can verify the protocol. Let me go on to the next view. I'll get to that as time progresses. If you go to put a clock in the car, and you go and keep the cars synchronized, so the cars both know the time they're at within a very small amount of time, the obvious thing would be to say, well, I can coordinate the movements of these vehicles. They're both going to turn at the same time. They're going to make room and stuff like that. But what we're doing is going a bit further than that. There's two things you have to do in order to prove that a system is going to operate safely. The first thing is verification. You've got these protocols, which are ways for different devices to interact, that are in different devices, and you've got to make sure that they're not going to do anything bad. They're going to interact together properly. That's the verification problem. The second problem is the conformance testing problem. You've got cars that are made by Ford, cars that are made by Mercedes, and you want to make sure that the systems in these cars are going to work together. And that's the conformance testing problem. So we plan on making all the cars work together except BMWs, because BMW drivers don't listen to anybody. The verification problem in cars is difficult because most protocols operate with timers. Something happens, you transmit a communication message. If it doesn't get through, 1 second later you try to message again. But if you're using these timers to set timers for when the cars are going to do things, depending upon how many chances it takes to get things across, the timers may be set at different times and do different sets of interactions. And these different sets of interactions cause different possible execution paths, and it makes it more difficult to prove that none of the paths are going to cause a problem. The second problem in conformance testing is that the conformance tests that have been developed for a specific type of finite state machine. They don't involve time. And when you insert time into this problem, you can't really use the test the way they were designed. So what we're going to do is we're going to show you how to use time to reduce the number of sequences in verification, and also to use time in conformance testing to come up with a strategy that allows us to use the techniques that have been developed in this new environment. Okay, what's probabilistic verification? This is something I worked on in the 80s. What it is it's a way to look at all the possible sequences that a protocol has gone through. I'm not going to go through all of this, don't worry. I've got an example that I'll use to show most of what's going on. But basically what we do in probabilistic verification is we try to say these different guys are interacting, and depending upon the messages they get back, they're going to do different operations. And we want to test every possible sequence of operations they're going to go through and make sure that every possible sequence is reasonably correct. Well, not every possible sequence. This work actually originated from something I did starting back in the 60s. I worked on the first communications protocol called DCCP1, Data Communication Control Procedure 1. It was also the IBM SDLC protocol, and it was used for 10 years before people realized it didn't work. And the reason they realized it didn't work is the protocol was used on something called the 2780 card reader, which most of you guys here have never seen or even heard of probably. But the thing was, it was a mechanical device, and it failed every 5 or 10 minutes. You had to reload the cards. The protocol failed maybe once every day or two. So nobody noticed the protocol was failing until they got more reliable devices. Now my philosophy has always been that the protocol doesn't have to be perfect. It just has to last longer than the machine. And actually, in recent years, I've even modified that a bit. I've said that the protocol doesn't have to be perfect. It just has to outlast me. And since I'm getting older, that's not as long as the machine. So what probabilistic verification does is looks at the interaction between machines. This happens to be a very simple communication protocol. It's a two-state protocol for a transmitter, a two-state protocol for a receiver, and it gets messages through correctly on a half-duplex channel. When these two machines interact, they create a much bigger composite machine. This describes the channel and what the protocols are doing. And it's this machine we have to test every possible sequence on. Now, what probabilistic verification does is it assigns high and low probability states to each of the transitions. So if we look at that machine, we've got one sequence of events that sends the message through very quickly at the top. And in a normal simulator, if this happens, if you get an error only once out of every million times, you go through that top sequence a million times before you fell down to the next level. In probabilistic verification, we put entries in a stack that correspond to one error. And after we've investigated the perfect path once, we investigate all possible paths with one error. We investigate all possible paths with two errors. And if these possible paths occur 1 in a million times, or 1 in 1,000 times even, and if they execute it once a second, If you go down to 3 or 4 levels, you're down to the point where you can guarantee this machine won't fail during the life of the universe, which is probably sufficient. And that's the whole idea of probabilistic verification. We're not mathematicians. I'm an engineer. I don't worry about proving things are perfect and will never fail. I'm happy if they won't fail before I do. Okay, the problem with probabilistic verification is that these paths can become very long, especially if you're doing something more complicated than a two-state machine. If you're doing an assisted driving protocol, which is what I've applied this to later in the talk. And so what we're interested in doing is reducing the number of states. Now, when time occurs, as I said earlier, you've got the possibility with timers of different sequences of events depending upon when the timers were set. However, if you said that this timer is going off at 2 o'clock, 1 second, and 35 milliseconds or whatever, it's going to work. You know, it's going to go off once. There's only one sequence of events you have to look at. And by having only one sequence of events, I can reduce the number of sequences I have to look at, and I can test things that are for a lot higher probability of failure, a lot lower probability of failure. The composite machine is still pretty big. In communications, when you look at the internet, we've created a stack protocol in communications. And we verify that one protocol is going to work depending upon the protocol working underneath it. We've done the same thing in assisted driving or automated driving systems. However, in these systems, there's a lot more ways to interact with the real world. In communications protocols, the only way we interacted with the real world was over the channel, and we're only worried about the probability of failure. In assisted driving systems, we've got to worry about the probability of sensors failing, the probability of the automobile failing, the probability of some jerk in the BMW is going to pull in, even though after we've made a space for ourselves. It's all that sort of stuff. I don't know why. I really hate BMW drivers. It has nothing to do with BMW not giving me funding. Okay, so what we did for the system is in communications, we have the communication stack, which separates the physical layer from the MAC layer, from the higher layer protocols. And we prove one protocol works based on another. We've done the same thing for assisted driving systems. The application layer, which is where we're putting our assisted driving operations, is the origin of a multi-dimensional system. I can actually draw 4 or 5 dimensional systems. I used to do it for threshold logic before digital logic 1. And I can do it here because we've got discrete layers in the protocol, but I'm not. Doing it this way is complicated enough. For each of these things, each of these interactions with the real world, we're going to set up a stack similar to the stack that we have for communications. In the case of the sensor stack, there are different kinds of sensors in the vehicle that detect where the other vehicles are and whether there's obstacles and such. And we've also put an inter-vehicle connection stack protocol on top of that. And what that does is it guarantees that all the vehicles are going to use the same sensor data. This way, if your vehicle tells you you're only 15 feet from the car in front of you, and yours say you're 20 feet from her, we're better off taking your measurement. We're less likely to bang into each other. So if all the cars are operating with the same numbers, they're going to be safer. There's fewer ways for them to fail. We have the clock stack, because we require this accurate clock for probabilistic verification to reduce the number of entries. And the clock stack consists of GPS crystal oscillators, because in New York you do have these canyons and you do lose GPS quite often. But part of the project that we worked on with the MTA that Umit didn't mention was we went all over the city. They gave us a bus for a walk. And we actually measured where we had signal and where we didn't have signal. And there's a lot of places in New York where you don't get signal. And there's a lot of places in New York where you get reflections, and it tells you you're in the East River. By the way, you should use Google Maps to put you back in the island. Now, Google Maps works for all of this stuff. And we also look at the operational computers in the automobile. If the brakes fail or something like that, we want to prevent somebody from pulling in front of us in a merge protocol. And a simple example of where deadlines first gave us an advantage. In order to do a merge between three cars, you got to get these three cars to agree they're cooperating, and the other cars aren't going to cooperate. So you need to get a lock protocol, which says that these three guys are going to work together, and they're not going to stop working together until they all do. Because if one of the guys stops and the other one doesn't, it creates a dangerous situation. So what we did was we set the lock, and this was actually Brian's protocol, the guy in the back. So if you have questions about this, go bother him after the talk is over. But what this does is it says, okay, rather than start creating a lock that says it's going to last for 10 minutes, we'll create a lock that says it's going to last for 2:05, and so on. And once people get the lock, they're going to agree not to give up on it till then. So they can't start to cooperate with someone else. Even if one of these cars leaves the roadway, it won't bother the other cars. Eventually they'll give up the lock at exactly the same time, and they'll continue doing something safe. They'll be able to collaborate with someone else. Nobody's going to give up the lock early because he happened to have required 3 communication tries to get the lock, and everything works fine. So it actually wound up being a very simple protocol. Brian proved it worked for this 8-car example, where 3 cars have to get the lock. The interesting thing about this is the competitive technique to using absolute time is something called time to automata. And the packages for time to automata, although they've been around for 10 years, can't handle more than three participants at a time. We're handling 8 at the very beginning, and we haven't even started optimizing this. So we can go a lot further, an order of magnitude further than has been done so far with just using timers. Okay, the conformance testing. This is the part that Umit worked on in my department. And now I'll tell him how to do it right. In conformance testing, what you do is you've got a device that was built by one guy. And you've got to find out if that box implements the protocol. You don't care how it interacts with other guys right now because we've already verified that it's going to work properly. So as long as you built this device, it's programmed properly, it's going to work properly. That's what we depended on. And we use a black box test, mostly because when manufacturers bring stuff to you, they don't like the idea if you cut it in half. So you take a black box, you put inputs in, you look at the outputs, and you say this, yes, this does do it, even though it doesn't do it. And for a finite state machine that just has transitions, this is a reasonable thing to do. That model doesn't handle time. There's no input here that says it's 2 o'clock. If you put a lot of timers in here, you can't use the techniques that we use. So what we're doing in our implementation strategy is we've said that we're only going to use absolute time, and our absolute time is going to be stored in a shared memory that says that the shared memory operates in such and such a way. And when we want to test the transition that's caused by absolute time, if we want to test it right now, all we have to do is write into the memory, and it executes. So we can use time the same way we had the other inputs. So it actually winds up being a very easy way to include time in some very complicated protocols. Yeah, in the past, if we were going to do this, we had to go to the edge with a time. In order to use an exercise of timer in a protocol, we had to go to the edge where the timer was executed. We had to come back here and then wait for the timer to expire. So we had to set the timer properly and all that. And that's a problem, especially going back and forth. You've got to use other edges that have timers in them. So it's possible to get into very difficult, long sequences, but just setting the memory winds up being a very easy way of doing it. Okay, so what do we use this for? We created a driver-assisted merge protocol. I don't believe in cars that drive themselves. I do believe in cars that help you. I mean, if you buy a car now and you get two cars close to the car in front of you, it does stop. If you try to change lanes or drift out of the lane, it does warn you. If not, I guess the German cars actually force you back in your lane, but the American cars just warn you. That's a difference in the way people are going to behave. Germans like being told what to do. In the driver-assisted protocol, the driver is going to signal his intention to merge, which tells the cars, gets a lock, tells the cars next to him. The advanced cruise control systems in these cars create a certain distance based upon your speed. The merge operation tells them double that distance plus 20 feet, so you've got enough room for your car also. And then when the gap is achieved by the automatic cruise control system, the driver is told, okay, you can pull in. Or if for some reason the protocol is aborted, a light goes off and it says, driver, you're on your own. If you want to merge now, it's your business, but we don't recommend it. And we consider this protocol to fail if at any point the driver is told you're safe to move in, and it's not. So this actually assumes that the lock protocol exists to prevent the one of the cars from dropping out and starting to work with someone else. What we did is we used probabilistic verification to prove that this protocol wouldn't cause an accident. And we did it under a number of different situations. We did it under the communications failures or even the loss of the communications channel. So like the communications protocol, we considered different numbers of communication failures. We considered inaccuracies of the sensors. So if there's a disagreement in the sensors and we can't create a collaborative view of the world, we either said we can't create a collaborative view of the world, we use a safe view. In this verification, we said, well, if there's a big difference, we just assume somebody's sensors isn't working, you can't work with it right now. We considered clock failures, where this clock that we have suddenly stops running. You know, if you've got a clock that's going to go off at 2 o'clock, and your clock stops, you might do something dangerous if you think it's still before 2 o'clock, and actually it's almost 2:30. And we also considered interference from aggressive drivers and emergency maneuvers resulting from obstructions in the roadway. So in conclusion, what we did is we showed that synchronous protocols in the multidimensional architecture we have makes it possible to verify these protocols. We also showed that a shared memory implementation allows us to guarantee that different manufacturers' implementations are going to work together. And that's basically what we use GPS for, as opposed to position, which is different than everybody else. Thank you. Any comments?
Very interesting talk, thank you. Can you elaborate a bit on how much you would depend on GPS and how much that might be a single point of failure? You mentioned that you can somewhat tolerate clock inaccuracies at the end, but I could imagine, for example, GPS jamming is relatively prevalent among truck drivers, that you have outages there, and how much would that cost you?
Well, that's one of the things we tested for. He asked how GPS failure might cause a problem with this, and that is one of the things we tested for. We said that, okay, one thing that might happen is your clock might just stop. Well, we've got a crystal oscillator in here which keeps the clock running at some rate, so just because the GPS is blocked, I mean, GPS gets blocked in Manhattan if you go past the big building, so you've got to be able to survive that. But if the GPS clock stops completely, the protocol we happen to be using in this is a time token passing protocol, which says that every so often something has to happen. And if it fails to happen, the system aborts. So if the clock fails at any time, it's okay. The clock failure was one of the failures we considered. As I said, we considered 5 different types of failures, and clock failure is an important one. You can't depend on anything working. We didn't depend on the brakes working. We said that you could have drivers who aren't participating in this, and they see a big gap, so they're going to pull into the gap before you. It's especially true of BMW drivers. You know, there's a whole bunch of things that can happen, and when the Google car doesn't consider this. I mean, the first time that the Google car kills somebody, they're going to take it off the road, I hope. I would hope they would take it off before then, but they're not going to. Any other questions? It's on.
Regarding the Google cars, I mean, can you comment further? Like, you think the technology is never going to get there, even?
No, I don't think the technology is never going to get there. I think the Google cars are going to happen in the future. I'm afraid of the way they're happening. Right now, these systems are being designed by some very good computer hacks. And computers are notorious for having undetected failures until the failures occur. And I think in something that you're betting your life on, you need more than that, which is why I think that it's very important to insist upon these systems being verified and being provably safe before you put them on the road.
More like reliability. More like reliability. You make them more reliable.
It isn't just more reliable. It's a matter of there are odd things that happen. There are things that happen once every 10 million times. If in one in 10 million times your brakes fail, that's a bad thing. You know, as long as the brakes don't fail before the car does, it's okay. But if your brakes don't last as long as the car, that's a problem. Any other questions?
So I know that in Michigan they're currently piloting, they have a safety pilot program. And in your mind, I'm hearing concerns about the proven safety. And this is a very short-term experiment, and I know the analysis won't be released until August, but from your perspective, what do you think is an adequate amount of time to analyze the safety data that would result from test piloting the 3,000 fleet experiment?
2 million years. No, seriously, I actually wrote a letter of complaint to the director of the Department of Transportation. I think the Michigan experiment is ridiculous. Just because you build something and put it on a test track and it goes around the track 10 times without anybody dying doesn't mean you're going to put it out in the road and have it last with 10 million cars for 100 years without anybody dying, which is what the real objective is. The objective isn't to say that, okay, it's gone around the test track 10 times, it's not going to kill anybody right away. Providing there's nobody else doing this. You know, I think that the way people are doing things right now doesn't make any sense. I would like to get a joint petition by this entire group to the Department of Transportation to tell them to push Lake Michigan back into the lake. Any other questions?
I think that's time.
Okay.
Yeah.
Thank you.